All right, Calc 30, 10.2. The title of this section is called Area Between Curves. So we took a look at how to find the area underneath a curve, a graph, or a line, and above the x-axis. And now what we're going to do is we're going to find out how do we find the area between two curves. And an example of this would be, here's an example that would be a good one to consider. So what happens if we have a graph of y equals x squared, which is a typical standard parabola with the vertex at 0, 0, and another graph that's overlapping that, that's on top of that, that's y equals 2x minus x squared. Now, we're going to have to sketch some graphs here because we're going to have to find a couple things. The first thing we have to find out is which graph is on top and which is underneath for the section. So let me just explain why we need to know that by just showing you this little graphic on the side. I'll just move this over a bit. So this example right here, remember we did this in 10.1. What we did to find the area underneath, let's say, the y equals sine x graph from 0 to pi, let's say, that's where it would be above the x-axis. What we are doing, in effect, is treating the sine x graph as the upper function. Okay, the upper function. And y equals 0, right here, as the lower function. So what happens if this lower function changes? Well, instead of subtracting 0, we would subtract whatever the lowest function is. That's what we end up doing, okay? So think about it. If we find the area, let me just erase this for a second. If we found the area underneath y equals sine x, and above the x-axis, that would be this. And if I found the area underneath y equals 0 and above the x-axis, well, those are the exact same lines. So that area is 0. So in a sense, if we consider two functions, an upper function and a lower function, what we've been doing this already. Now, if this lower function were to move, we would have to adjust the area. So for example, what happens if we had y equals 0.5, let's say, okay? That would be actually technically, let me draw that a little bit better. That would be really halfway between 0 and the maximum of 1. So if I wanted to find the area between these two curves, I would have to somehow adjust what my lower function is, and I would have to get rid of this part right here. I'd have to get rid of that. Okay. So if I did that, then it would be kind of like I'm subtracting the area under 0.5 and above the x-axis. So if we have one function, here's the x-axis, if we have one function doing this, the antiderivative of that function evaluated at b minus the antiderivative evaluated at a, like we learned in 10.1, gives us the entire area in between those two. Now if we have another function, let's say this function is moved up, this area is going to decrease. By how much? Well, by the area that would be underneath this lower one. So, having said that, let me just now continue some of the things we have to determine when we're finding the area between curves. So we'll come back to this, okay? This is going to be a big part of what we're learning today. So first of all, we must determine which is the upper curve, that's the top curve, and which is the bottom curve. So in our example 1, the top curve is actually this one right here, if we're talking about this area between the two. You see, this one is the upper or the top curve. The lower curve in this region where we're interested in, this is the lower one. See that? Now why is that important? Well, because we are going to want to find the area underneath the top curve and subtract the area underneath the bottom curve in order to find this remaining area. So we must determine upper curve and lower curve. The second thing we have to determine is where are the intersection points, or if there are any. Because in our example here, we have two two graphs. I'll just redraw this a little bit here. We have two graphs that intersect right here. And so the question probably won't tell you between this A value and this B value. It might not say that. It just says find the area between the two curves, like enclosed between the two curves. So you got to figure out where that starts and where it ends. And the key there is the intersection points. This point right here, and we know that's 0, 0, and this point right here, and we can find that out. So how do we find the intersection points between two functions? We let them equal each other and then solve for x. So we just let them equal each other, solve for x. If you have a graphing calculator, it may be appropriate to do that. So you would graph the first one, graph the second one, and then identify the intersection points like I taught you before with your graphing calculators. Okay? Chances are on an evaluation, if you get a question like this, you're probably not going to be able to use a graphing calculator. You're going to have to find the intersection point yourself. And in this case, that's not a big deal. Was it 2x minus x squared equals x squared, right? If we let them equal each other, we have 2x equals 2x squared when we add x squared to both sides. X equals x squared. Where does that occur? Well, that occurs at 0 and at 1. Or if you want to do it this way, 0 equals x squared minus x. And factor that. No, I wasn't planning to do this. Sorry. I'll make some more room. Okay. If you wanted to factor it, then this would be 0 equals x times x minus 1. And your two intersection points, or the two solutions to this, right? The solutions to this would be at x equals 0 and x equals 1. So you've got 0 and 1. Guess what? That's your A, and that's your B. So which one is upper, which one is lower? You're going to have to maybe sketch. Where's the start point and end point for this area in question? You're going to have to find out intersection points. Now, for some questions, they'll give you a graph, and they'll give you the intersection points. Easy. Some questions, you'll have to find everything from scratch. Okay? So that's the essence of what this lesson's about. Let me show you some examples of what you might run into, guys. Okay? So here's an example between what looks like a sine graph and a straight line. So if we were asked to find the area enclosed between these two graphs in example 1, then I would have to find out where the intersection points are between these two and which graph is actually on top during that part of the domain. But that would be a visual of what we're trying to look for. Now, not all questions are like that. It's not, here's two graphs graphed simultaneously and there's an enclosed region. Sometimes it's just, hey, what's the area between two graphs? And they might give you A to B. So you might have a case like this where you have two graphs that don't intersect, but they're telling you, hey, I want you to find the area between the two graphs, okay, from A to B. I don't know if that's exactly the way it was, actually. Let me just say it like this. Okay? So what you'd have to do then is, first of all, you'd have to figure out which is the upper and which is the lower between A and B. And again, a quick sketch would help. You determine that. And if one graph is always above the other over that domain of A to B, then it's easy then. Then you find the area underneath the upper graph, because that's this area. And then you find the area underneath the lower graph, and you subtract them. And that will give you the result of this area in between. Okay? So we've talked about enclosed area, find the intersection points, figure out which one's on top. Antiderivative of the one minus the antiderivative of the other. You're good to go. With this one here, where they don't intersect, you'll probably be given an A and a B. And then you have to just figure out which one's on top. Find the integral underneath the top one minus the integral underneath the bottom one.
In what ways are they different? How would you be able to find that?
Well, there's no intersection point, for example, too. So these are different in that there are no intersection points. So you would have to be told what the A and B is, right? If it just says find the area between these two curves, first of all, it's not enclosed. Second of all, it would be infinite, I guess, because it goes on, it's just how much area. They don't touch. So it would have to be, have to give you some kind of enclosed domain there. That make sense? That help? Yeah. Okay, example 3. This is another different looking one. What if you have one graph that's on top, great, and the other one is completely on the bottom, but it's negative? It's negative. What do you do there? Well, here's the thing. Here's the nice thing about this. As long as from A, this is A, to B, this is B, as long as from A to B, if you have the same function being on top and the same function being on the bottom, you do everything the exact same. So you take the area on top, or the area of the upper curve, and in this case, visually, it would look like this, right? It only goes down to the x-axis. And if you subtracted the area of this graph, remember, this is a negative area under here, isn't it? When you do from f of b minus f of a, it becomes a negative. So if it's like having a positive area minus a negative area, and guess what? They end up adding. So you end up getting a large positive there. And as long as one graph is always over top of the other graph, it doesn't matter where it is, above the x-axis, below the x-axis, it doesn't matter. Okay? So I'm just going to maybe, I think I have some notes here. I was just going to think if I should tell you about this now or just jot this down now. Whoa. Okay, no, that's method 2. Let me just jot this down here now. I thought I had this typed out neatly somewhere else, but I do not. So in this case, in all these cases, if one function is always the upper function over the domain, you just simply do the area underneath the upper function minus the area underneath the lower function between A and B. It's always how you do that. Okay. The only tricky part comes when if you're given, that's the example 4 here, okay, if you're given this type of question, then the same function is not always on top. So I'm going to just pause here for a moment. And if we had something like this, we have y equals sine x plus 1 as one function. And then y equals sine of x minus 1. That's a sine function that's shifted over to the right. And you want to find the area between the two functions from A to B. If this was the question that you get, you can see that we kind of have to solve two different problems and add them together, because at some point right here, from A to some point right here, one of the functions is upper, but then that flips for the second part. So again, as long as you can identify which is the upper function, it's really easy. In a case like this, you're going to have to graph, and you're also going to have to find the intersection point. So you need to find out what this C value is. And then you would do area 1 with this graph as being the upper function. And I'll use a different color here, like dark green. So area 2, this one, you see now this graph is the upper function, you see? So you're going to have to do kind of two separate questions at once if they overlap and get crazy like that. So that's probably the most difficult one that you'll see, but we need to be prepared for it. Okay. If you're dealing with a cubic function and a straight line, you could run into the same thing, right? Where the cubic function comes up and then it goes down and goes back up again. And you have a line through the middle, and then the cubic function's on top for this section, and then the line's on top for this section. So you just have to, graphing it does become pretty pretty important. At least a rough sketch so you can kind of see how it looks. Yeah.
How do you know that it's not that triangle there that you're finding? Like.
Well, okay, so so this question, I didn't write out the question for you, but this question would be, what's the area contained between the two graphs from A to B? So this area down here, like this is one you're talking about, that area is only underneath this function and then underneath this function. It's not between the two. So the question would read something like, determine the area between the two functions from A to B. And so that would be clearly, this is an area between function 1 and function 2. This is also an area between function 1 and function 2. Okay? So that's what this question would read. So the question for this example might read, find the area enclosed between the two functions on the interval A to B. Remember the closed brackets there? That notation is kind of like interval notation there. So between x values of A and B. So that's what the question that might go with this example, okay? All right. Ooh. Okay, let's do something fairly straightforward. This is a very simple one. So why don't you write this question down as an example. I'll give you a moment to do that. It says, if you want to just write this while I read it, it says find the area between y equals x squared plus 1 and y equals x from x equals 1 to x equals 3. Yeah.
So I'm just trying to understand this correctly. If they don't, trick question.
It'd be a trick question if they did that. Yeah. Okay, so find the area. Now, sketching, rough sketch, again, this is pretty easy to do. You know about transformations from Pre-Cal 30. You have a parabola here, and then you just bump it up 1 unit, right? So again, a rough sketch gives you that. A rough sketch of y equals x, you would be able to tell that this line, y equals x, that would go through 0, 0. That should go through 0, 0. It doesn't look like it does in this diagram. But that would be a line that would be underneath that parabola. Okay? So a rough sketch, you should have an idea that this is the region you're looking for, the area of this region. Why that region? Because that's the region between x equals 1, so the vertical line of x equals 1 would be kind of the cutoff on the left, and x equals 3 would be the vertical boundary or cutoff on the right. And so if we consider that, we're bounded by the parabola on the top, the line on the bottom, and the vertical lines of x equals 1 on the left and x equals 3 on the right. So we have to find that enclosed region. So the start of the solution is here on the screen. So let's take a look at what they say. We sketch both curves, identify the required region, and note that the parabola x squared plus 1 is always above y equals x. So that's very important. That's what we need to understand. Which one's on top over this interval? If they overlap, like if they switch being on top for some reason, then we have to split that region into at least 2 parts to find the separately. Because we can only work with, this method only works when we know what the function is on top. Okay? So, again, this is pretty straightforward because all we need to do is we need to find the area underneath this single curve, the parabola. We need to find this total area. That's the first thing we need to do. Find this total area. Then, we know we don't want this whole area. What we want is the area that's left when I subtract this area, which happens to be the area underneath the line. So we take this away, and then we're left with what we want. So for this parabola, we do f of 3 minus, and when I say f, I mean capital F, of 1. I find that area. Then I big subtract, right? F for this one, I'll change colors actually. Let's go to black. For this graph, I do f of 3 minus f of 1, right? Because those individually are the areas underneath each individual curve. So when I big subtract those, then I get my r, right? That's r there, I see. All right, so it's going to be a pretty good idea for me to find what is the antiderivative or the integral function, the antiderivative function of this red one, of this x squared plus 1, right? So capital F of x for the red parabola function is what? What does that look like? 1/3 actually, close, 1/3 x cubed, okay? So you can bump the exponent up first to 3 and then divide by 3, whatever is best for you. Plus x, right? And then because these questions where we're actually getting a number answer, this is not an indefinite, we don't have to do plus c here, okay? If we did plus c, we would be subtracting a bunch of things, so the c's would go away anyways. So we don't have to do plus c. All right, that's excellent. Let's figure out what capital F of x is for the line, and that's going to be pretty easy. That's going to be what? Just the 1/2 x squared. You get that? It's a 1 there, so we add 1 to make it 2, and then I divide by 2. All right, everybody's with me so far? Okay. I'll try and color code this again. So let's find the area underneath the parabola. That's going to be capital F of, well, I've got that written over here. I won't rewrite it. So let's just go ahead and solve this. So it's going to be 1/3 3 cubed plus 3. You see, I've just inserted 3 in for x there. Minus f of 1. So I'm going to go 1/3 of 1 cubed plus 1. What's that going to be? This right here, let's evaluate this. That's going to be 27/3 is 9 plus 3 minus 1/3 plus 1. So that will give us 32/3. Okay, so now what we do here for the black one is I'm going to go 1/2 of 3 squared. There's just one term there, so that's nice. Minus 1/2 of 1 squared, which is 9/2 minus 1/2, or 8/2, or 4. So the black one is 4. Okay, so 32/3, so my total here, my answer, R, the area of R is going to be 32/3 minus 4, which is 20/3 is correct. And that's going to be just units squared. Well, it's not super hard if you if you sketch it out and you kind of see what you're doing. It's really like calculus is mostly algebra. It's just mostly algebra. Yeah, the finding the antiderivative function, yeah, that's calculus. But mostly it's algebra.
This is what I mean, you don't have to think. I know you have to think, obviously. But it's like, you're plugging in numbers.
It's a different kind of thinking, isn't it? Okay. All right, so we are, let's see, what have I got left for the, I'm going to have to save method 2 for tomorrow, because we only have 10 more minutes left. All right. So grade 12s, stay with me. We've got 10 more minutes here. We got to finish this, okay? Example 3. You like my new clock? Yeah. We don't have quite 10 minutes left, so we got to get rolling. Example 3. This is the example where the two graphs kind of overlap each other and they crisscross. And so we have to split this area in between these two curves into two sections, R1 and R2. So the example here that will end this first half of the lesson is find the area of the region between the curves, y equals sine x and y equals cos x, from 0 to pi/2. First thing we want to do is do a rough sketch of each of these. This is the sine x right here. That's this one, sine x. And this would cross over here at pi. And the cos x is, I'll put this in red, that's cos x right there. And that would cross at pi over 2. So 0 and pi over 2, those are our left, that's the left boundary and the right boundary. So the issue here is that we can see by graphing it is that there isn't just one function between 0 and pi over 2 that's on top always. So we always need to, we need to keep in mind that we need to separate this into 2 blocks. Okay, 2 blocks. And the block 1 would have cos on top. All right. So we have to find the intersection point. Okay, so where does sine of x equal cos of x? And for this kind of thing, you have to think about the unit circle. Because you can't just get x by itself. And yeah, sine and cos are the exact same, right here, there's the coordinates, at pi over 4, which is included in this diagram here for you. Okay, you see that's where it intersects, and you might have to use the unit circle to determine something like that. Okay, solving trig equations involves the unit circle lots of times. Okay, all right, so that means that I need to split this into 2 pieces, and R1 I'm going to be able to find by going from 0 to pi over 4 only, and cos is going to be on top, okay, for that one. So we'll do, let me just check notation. There's going to be a convenient notation that I don't think you guys know about yet. Okay, well, we won't get too fancy with notation here just yet. So we're going to do the area under the cos is going to be f of pi over 4 minus f of 0 for cos. And then for sine in blue, it's also going to be f of pi over 4 minus f of 0. Yep.
Sorry, what is the sine x equals cos x indicating?
That's what we use, the sine x equals
Oh,
cos x,
okay.
just to find the intersection point. So I'm going to erase that now. Okay, so cos x, right? So cos x is in red. What's the antiderivative of cos x?
No, sine x.
Positive sine x, right? That's the tricky one. So we're going to do sine of pi over 4 minus sine of 0. That's how we're going to find this area all the way underneath that cos. So sine of pi over 4 is root 2 over 2. Sine of 0 is 0. So this equals just root 2 over 2. And then we'll do the same thing for the sine function. So the antiderivative of sine is?
Negative cos.
Very good. Negative cos of pi over 4 minus negative cos of 0. Make sure you have minus there. So this is negative root 2 over 2. And this is plus, what's cos of 0? Cos of 0 is 1, actually. Yeah. Which is going to equal 1 minus root 2 over 2. Or, yeah, I guess you could just leave it like that. So this R1, right? R1 is going to be root 2 over 2 minus 1 minus root 2 over 2. Because that's the top, and then here's the blue bottom. So that's going to be, well, you've got root 2 over 2 plus root 2 over 2. So that's just root 2. And minus 1. Root 2 minus 1. So that's R1. And we're half done. Isn't that great? So now, from pi over 4 to pi over 2, I have sine being on top. Sine of x is the upper function there. So, R2, D2, R2, we're going to go f of pi over 2 minus capital F of pi over 4. And then we'll also do capital F of pi over 2 minus capital F of pi over 4 for the lower cos function. So we know what the antiderivative of sine is already. So that's going to be the negative cos. So cos of pi over 2 is, looks like 0. Cos of pi over 4 is root 2 over 2. So that's root 2 over 2. Sorry, I don't have all this on the same screen. I'm trying to keep it large for you, but I could increase that a bit. And then in blue over here, I guess that's going to be your cos here in this area. So the antiderivative of cos is positive sine, so sine of pi over 2 minus sine of pi over 4. Sine of pi over 2 is 1 minus root 2 over 2. So R2 is going to be a root 2 over 2 minus 1 minus root 2 over 2. And does that look familiar?
R2, 2.
No? 2 over 2 minus 1. So that's the same as R1 there, isn't it?
Oh, it's crazy. But we already knew that the areas were equal, so do we have to use it?
Well, did you know the areas were equal?
Because it's cos and sine are opposites, right?
Well, cos and sine aren't opposites. They're shifted. They are shifted.
Well, there's
Okay, well.
there's no there's like no
Yeah.
transformation on the graph. I'm on the right
Yeah. So you might have determined that the R1 equals R2. It wasn't given. But yeah, I mean, this is a symmetrical, like these are perfectly symmetrical. So R1 does equal R2. We've proven it. So if you know for a fact that R1 equals R2, you could just do R1 and times 2 to get the area. Yeah. But here now we know for sure. So if you add these two together, so if you add R1 and R2 together, you have 2 root 2's, and then minus 1 is minus 2. So there is your total.
Crazy.
All right, so that's kind of the first part of 10.2. I'll do the second part tomorrow. Yeah, there is a second method of doing this that I'll explain tomorrow. It's not any harder. It does make things easier a little bit actually in some respects. So it simplifies things just a bit. Okay, so that's 10.2 part 1.